Hi everyone, so welcome back again. This is week 6 fundamentals of data science class. So we're going to discuss about the data splitting technique. Okay, so the session learning outcomes for today is to understand the types of data splitting technique, able to use the appropriate data splitting technique for a particular case, and understand the pros and cons of each technique. The agenda is the introductions and then the evaluation strategies. So if we want to evaluate the classifications model, we want to select the most appropriate learning schema for a specific problem. So how do we evaluate this? We evaluate its ability to generalize what it has been learned from the training set on the new unseen instances. So instead of we claim the performance of the model on the data that they already seen, we test them to a set of data that they haven't seen. So it's completely new data. So for example, this is our populations. We take a sample, a set of sample, we train this a model with this data, and then we come up with the accuracy. The accuracy said it's on 97% accurate for this training data. So if the model is general enough, then we can draw conclusions to the populations. So we can say, okay, so in the populations, the accuracy of our model can reach up to 95% using some statistical inference. So what is actually data splitting? Data splitting is a process used to separate a given dataset into at least two subsets called training and test. This step is usually implemented after pre-processing when the sample spectra have been corrected for noise or undesired variability. First, it's called resubstitution, testing the model using the dataset used in training. Resubstitution error rate indicates only how good or bad are our results on the training data, expresses some knowledge about the algorithm used. So we actually cannot draw any conclusions at all about the model. This is just the knowledge about the algorithm. The error on the training data is not a good indicator of performance on future data since it does not measure any unseen data. Why this is not a good indicator? Because new data will probably not be exactly the same as training data. It can be something different, really different. Also, we don't want our classifier to be underfit or overfit. We want something in the middle, general enough to classify the new data, but not too general and not too specific. The second technique calls leave one out. Leave only one instance out and train the data using all the other instances. And then repeat that for all instances. Then what we can do is to compute the mean error. That's the model performance. So for example, this is the data. We take only one row or one data point as our test data, and the rest will be our trained data. And then we repeat multiple times until every single data in this set has been tested. The second technique calls holdout. The large datasets can be divided into two subsets, one for training and the other for validations. The common practice is to train the classifier using 2/3 of the datasets or 70% and test it using the unseen third or 30%. We can also apply repeated holdout method, which is process repeated several times with different subsamples. Error rates on the different iterations are averaged to give an overall error rate. And then the next technique called k-fold cross-validations. You need to divide the data into k equal parts or folds. One fold is used for testing, while the others are used in training. The process is repeated for all the folds and the accuracy is average. So 10-fold cross-validation are most commonly used. Even better, we can do repeated cross-validations. So this is the data. This is the total number of examples. We cut every part of it, and then we call this as k. For example, we cut the data into 4 different subsets. So one subset, second subset, the third subset, and the fourth subset. So iteratively, with the k-fold cross-validations, we use first subset as the test sample, and the rest will be the training samples. And then in the next iterations, we use the next subset as the test data, and the rest will be the training data. And then we keep repeating the process until all part of this test example has been evaluated. The next technique called Bootstrap sampling. Cross-validations use sampling without replacement, so we cannot test same particular data. Yeah, we always use the different set, yeah, for every iteration. So this is different with this one. This is different with this one. But with Bootstrap, they use sampling with replacement to form the training set. Sample a dataset of n instances n times with replacement to form a new dataset of n instances. Use this data as a training set, and then use the instances from the original datasets that don't occur in the new training set for testing. So similar with cross-validation but with replacement. Okay, so are train and test sets enough? This is the data. And then with the known result, we take some of them as the training set and some of them as the testing set. And we start building our model. And then we come up with some classifier. It can be either a formula, it can be either a tree, whatever we come up with, this is our classifier. We test the data from here, the one that got taken from the population, from the samples data, and then we come up with the predictions. Okay, so first line, this is positive. Second line, oh, this is negative. And the third line, it is positive. Okay, based on these predictions returned by our model, by our classifier, we can evaluate whether this model is good enough or not, general enough or not. Whether it already reached the desirable performance or not. If not, we need to tweak or tune our model, and then it keep repeating like that. So actually it's not enough. We need the third set, which is validation. In some cases, we need validation as well. What is validation actually? The validation is actually another part in here, which is called validation set. This is to tune the model before We test them with a really new unseen data. So we have the final evaluation here. This is the one that we can claim this is our model performance. But before this, we have a validation set here in the middle of the process. Okay, last thing, the problem with imbalanced datasets. Sometimes in classification model, in classification problem, we have data with imbalanced classes. One class for animal and the rest probably for plant. So the number of the class can be imbalanced. This can cause a bias. Machine learning can ignore the minority class entirely. So we don't want something like this. Especially when the minority class is the important class. So we can do two techniques, which is undersampling and oversampling. Oversampling is we copy the minority class, and when we generate the synthetic datasets based on these facts in here, we generate synthetic datasets, or we can resample datasets and then we just copy so that the minority become as large as the majority. Or we can also perform the undersampling. For example, this is the minority class and this is the majority class. We need to sample this majority class in order to fit and match the size of the minority class. So our dataset will be very little. So this is some oversample techniques. You might try each of these, and then you can discuss and report. So this is the discussions. Find the pros and cons using data splitting techniques mentioned in the slide. Learn about 7 oversampling techniques mentioned earlier, and find out which when one technique is more appropriate than another. Practice with one of the technique and show the result. Thank you.